All right, we're taking a look at the negative number identities. We saw how these things were facts. We also plugged in some real number values. We also took a look at okay, yeah, that was it. All right, we kind of jumped ahead and we took a look at the 3.1 section. Before we actually get into some of the problems, you'll just notice that in the homework problems, they have the identities embedded in the homework. Now, just taking a look at the formula sheet, we've already talked about the reciprocal formulas. We've taken a look at the quotient identities. And we've in a roundabout way looked at the Pythagorean identities. So before we go any further on the formula sheet, I just want to show how these things come into play. Okay. So from geometry, we have the Pythagorean theorem. Bless you. All right. We had a Pythagorean theorem. And you've probably seen it as a squared is equal to c squared plus b squared. As we first started out in the trig course, we didn't use c, b, and a. We use r squared is equal to x squared plus y squared. Bless you. So just to show where this comes from, and it must be a problem with me flipping the screen over something. All right, so I'm going to go back into the lecture notes really quick. And I believe this was in 8.3. Right, we talked about sketching out a triangle or an angle in the rectangular coordinate system. So we have that the sine is y over r, the cosine is x over r, the tangent is y over x, and then we have our reciprocal functions, right? We also had the Pythagorean theorem that was also followed along with this, which was r squared is equal to x squared plus y squared, right? So now in this next piece, I'm going to show how these things come about. All right. So we have r squared is equal to x squared plus y squared. So this is the Pythagorean theorem we've been dealing with. So if I take the Pythagorean theorem, r squared is equal to x squared plus y squared. And let's say I divide both sides by r squared. Right? So keep in mind from algebra, we have the properties of equality, and it says that whatever you do to one side, as long as you do the exact same thing to the other side, you're going to maintain equality. So I'm going to divide both sides by r squared. So if I divide the left-hand side by r squared, that's r squared over r squared. If I divide my right-hand side by r squared, I'm going to divide everything by r squared. Right, so what I've simply done was divide both sides by r squared, right, which is mathematically a legitimate thing to do. So now I'm just going to go and I'm going to rewrite these fractions. I can rewrite r squared over r squared as r over r squared. I can write x squared over r squared as x over r quantity squared. And I can write y squared over r squared as y divided by r quantity squared. So I just simply divided both sides by r squared. So now here's where the sine and cosine pop out. If I look on the left-hand side, anything over itself is 1. So r over r is 1, and 1 squared is 1. If I look back at my relationships, x over r is actually what? X over r is cosine. So I'm going to replace x over r quantity squared with cosine theta squared. I'm going to bring down my plus. And then y over r, from our relationships, y over r is the sine. So y over r quantity squared is sine squared theta. So that's that first Pythagorean theorem. They're just kind of written in a different order, but it says cosine squared theta plus sine squared theta equals to 1. All right. So sine squared theta plus cosine squared theta equal to 1. That's where that comes in. In order to get the other two formulas, it's just a matter of what you divide by. So I'm going to take the same r squared is equal to x squared plus y squared, if I can slide this over. This does not want me to slide it over for some reason. R squared is equal to x squared plus y squared. Let's say this time I divide both sides by x squared. All right, so I have r squared over x squared is equal to x squared over x squared plus y squared over x squared. So then once I simplify, r over x quantity squared is equal to x over x quantity squared plus y over x quantity squared. So out pops the next relationship. R over x, if I go back, r over x is going to give us the secant. So this is going to be secant squared theta. That's equal to, well, anything over itself is 1. So x over x is 1. 1 squared is 1. Plus y over x is the cotangent. So we have plus cotangent squared theta. And this is our next relationship. All right, secant squared theta is equal to 1 plus cotangent squared theta. So if you'll notice, this is the next relationship. All right. And then in order to get that third Pythagorean identity, we simply go back and we multiply, or excuse me, we divide both sides by y squared. Okay. All right, so as you look at the all exam formula sheet, okay, these first three Pythagorean identities, they're no longer written in like X, Y, and R. They're written in terms of sine and cosine. So now with that being said, when you're asked to simplify a trig expression, when you simplify a trig expression, you're not actually solving the problem. Only thing you're doing is kind of reducing it down into its lowest terms. The lowest terms of any trig equation would simply be to put everything in terms of sine and cosine. So you're going to see on a lot of these problems when they want you to simplify, it specifically says write your final answer in terms of a sine or a cosine. All right, so using this first set of identities, we don't really use the Pythagorean theorem too much in this first set, but let's take a look at some questions. What was the first one? I think this is the first one. Okay, and that's the reason we use trig identities is simply to simplify trig expressions. To simplify trig expressions means to condense your trig function as simple as possible, okay, or using as less trig functions as possible. So here is problem number 6. It says use trigonometric identities to fully simplify the expression. So whenever you're asked to simplify an expression, here are like a couple of strategies you could use. These are strategies to simplify. Trig expressions. The first strategy is to write everything in terms of sine and cosine. So that's the first thing you should do. You should try to write everything in terms of a sine and a cosine. The second thing you can do is you can factor trig functions. And you can also substitute. Okay. All right, so I'll kind of explain these separately. The first strategy is you want to write everything in terms of sine and cosine. So in this first section of Module 3, that's going to be our main objective, is to write everything in terms of sine and cosine, and then we can cancel common factors. You can also factor trig functions. Now we're going to get into factoring in the next, I believe it's the next to the last section when we actually solve trig functions. When you solve trig functions, you're using a combination of the identities, and you're also using some algebraic methods such as factoring, zero factor property, that sort of thing. And then the third thing you can do is substitute. Okay, so we're going to substitute, bless you, we're going to substitute some identities to simplify some of these trig expressions. All right, so let's look at problem number 6. All right, so it says use the trig identities to fully simplify the following expression. The sine of x times the secant of x times the cosine of x. The first thing I'm going to do here is I'm going to write everything in terms of sine and cosine. When you write everything in terms of sine and cosine, you're attempting to put the trig expression in its simplest form. Now, if you can't write it in terms of sine and cosine, that's okay. But everything that can be written in terms of sine and cosine, we're going to write it. So as I look at this expression, I have the sine of x, and that's already in terms of sine, so I'm going to simply bring that down. Times the secant. So if I look at my reciprocal identities, I can rewrite the secant as some type of cosine. So I'm going to rewrite secant x as 1 divided by cosine x times cosine x. I'm just going to bring down cosine x. All right. So now normally you would want to stay away from fractions, but in the trig class, sometimes fractions can be your best friend, right? We looked at a formula on how to simplify a complex fraction. And again, a complex fraction is a fraction where there's a fraction in the numerator and there's a fraction in the denominator. And then we can simplify using an algebraic formula. If I write out my trig expressions as fractions, this is going to allow me to like cross cancel. So remember, when you're multiplying fractions, we can cross cancel, right? Reduce any, cancel any factors, and then we can multiply straight across. So as I look at this, I can actually cross cancel my cosines. And what I'm left with is the sine of x. So we can simplify sine x times secant x times the cosine of x as simply the sine of x. All right, any questions about 6? That's right, because when you multiply, you can cross cancel. So I'm kind of writing everything as fractions and then canceling out the common factors.
So why did you put 1 over cosine x and then cosine x over 1?
Well, this is sine x. We've rewritten the secant as 1 over the cosine. And then I just brought cosine x down. And I just put sine and cosine over 1, and then I can kind of cross cancel. All right, that's number 6. Number 8, we're going to do the same way. So it says write the following in terms of sine and cosine and then simplify. Leave your answer in terms of sine and cosine only. Because you can get to a part where you can kind of keep simplifying and simplifying, but this actually wants you to write everything in terms of sine and cosine, and your final answer should only contain sines and cosines. All right, so let's simplify cosecant x divided by secant x. All right, so the first thing I'm going to do is try to rewrite cosecant and secant in terms of sine and cosine. All right, so if I look back at my identities, I can rewrite cosecant as 1 divided by the sine. So I'm going to put that in the numerator. 1 divided by the sine of x. In the denominator, we have secant x. So if I go back up to my identities, I can rewrite secant x as 1 divided by the cosine of x. So in my denominator, I have 1 divided by the cosine of x. So remember that formula that we were using in the last section? It says if you have a complex fraction, Then you can multiply the very top and the very bottom. And then you can multiply the bottom of the top and the top of the bottom. So that means I can multiply the very top and the very bottom. So 1 times cosine x is cosine x and then I can multiply the bottom of the top and the top of the bottom. So sine x times 1 is sine x. Now, since it wants me to answer in terms of sine and cosine only, this is my stopping point. So the reason why I say you can go a little bit further is because the cosine divided by the sine, that is also a cotangent. So in the problem, it tells us to leave the answer in terms of sine and cosine only. Okay. So for my problem number 8, I'm going to leave it as cosine x divided by the sine of x.
If you were just multiplying, how would you do tangent or cotangents in terms of sine and cosine? Or would they be the same as the quotient ones?
You got an example of the problem?
On the formulas that it gives us, like quotient identities and whatnot.
Oh, I got you.
Yeah. Is it only for dividing, or would that be the same as multiplying as well?
That'll be the same as multiplying. They give you 2 sets of formulas. Like for tangent, you can either write it as sine over cosine, or you can write it as 1 over cotangent. But since we're trying to put everything in terms of sine and cosine first, I would use these 2 versus the reciprocal functions. Okay. All right. Any other questions about number 8? All right. Number 10. It says add or subtract is indicated and then simplify as much as possible. Leave your answer in terms of sine and cosine only. So I have 1 divided by the sine of x is equal to 1 divided by the cosine of x. Okay, now that's like a simple way to explain the problem, and then there's like a algebraic way to explain the problem. So I'll kind of do it the simple way first, I guess. Whenever you add or subtract fractions, which is what these are, even though they're trig fractions. But beside the fact that they're trig fractions, in order to add or subtract a fraction, you must have a common what? Denominator. So if I look at my denominators, I have a sine and a cosine. So this is kind of going back to algebra. And it's to find the least common denominator The least common denominator is the factor or factors that have the greatest amount of appearances in any one factorization. So the least common denominator is the factor or factors that have the greatest amount of appearances in any one factorization. So in order to find the least common denominator for my problem, I simply want to write down all of my denominators. So my denominators are sine x and cosine x. All right. All right, so now you got to factor the denominators. Now, one thing about it, these denominators are already factored. So what I mean by factor, if you're trying to factor something, that means to rewrite whatever you're given as a product. So I can't factor anything, so my denominators are in lowest form, right? So when I factor out sine x, I get sine x. When I factor cosine x, I get cosine x, as they're already completely factored. So now I'm going to apply this definition. It says the least common denominator is the factor, so I have two factors, right, a sine and a cosine, that have the greatest amount of appearances in any one factorization. So if I look at my sine, how many times does the sine term appear in my first factorization? It's just once, right? I just got one sine. If I look in my second denominator, how many times does the sine term appear? It doesn't appear at all, right? The greatest amount of time that sine appears in any one of these factorizations is once. So I'm going to include it in my least common denominator only once. So next I'm going to look at my next denominator, cosine. The cosine appears once in this factorization. It doesn't appear at all in this factorization. The greatest amount of time that the cosine factor appears is once, and it appears right here. So I'm only going to use it in my least common denominator only once. So the least common denominator is sine x cosine x. All right, so I'm going to make equivalent fractions. So I have 1 over cosine x cosine x sine x okay. All right. So if I look at my least common denominator, if I look at my first term, this sine was multiplied by what to get the least common denominator? Cosine. Whatever you multiply the top by, you have to multiply the bottom by that same quantity. So since I multiply the bottom by cosine x, I have to multiply the top by cosine x. So 1 times cosine x is cosine x.
We only know that because we did the LCD over here.
Right.
If there had been a value as the x with the LCD have changed, when you say we see sin or cosine this amount of times, does that mean just like the word sin and cosine, or is that like if it was in 5 sins?
I got you. If we had like a square, so say if this was sine square x, you would factor that down to be sine x times sine x. But since we don't have any powers, these are already in simplest form. So when I make my equivalent fractions, this sine was multiplied by cosine, so I got to multiply the top by cosine. And then for my second term, this cosine was multiplied by sine to get the least common denominator. I got to multiply the top by that same quantity. So if I multiply 1 times sine x, I get sine x. So now when I add or subtract fractions, I have a common denominator, so I'm going to keep the common denominator. and I'm going to combine my numerators. So in the numerator, I have cosine x minus sine x, and that would be the solution. All right, any questions about 10? All right, so you should have cosine x minus sine x divided by cosine x sine x. Okay, and I'll just go to the next one. All right. All right, and then number 11. It says write the following in terms of sine and cosine, and then simplify if possible. Leave your answers in terms of sines and cosines only. So we have secant x times cosecant x times tangent x. So I'm going to rewrite each of these in terms of sine and cosine if possible. So I can rewrite secant as 1 divided by cosine x, because secant and cosine are reciprocals. I can rewrite cosecant x as 1 divided by sine x. And I can rewrite tangent as sine x over cosine x. So now since I'm multiplying, I can cross cancel. So I can cross cancel my sines, but I can't cross cancel the cosines because they're in the denominator. So now I can multiply my numerator. So in the numerator, I'm going to have 1. And in the denominator, I have cosine times cosine, which gives us what? Cosine square x. So notice that cosine x times cosine x is not 2 cosine x. Cosine x times cosine x is cosine squared x. Since it wants us to leave in terms of sine and cosine, this is our final solution. All right, any questions about number 11? It's almost like this seems kind of pointless. Like, why are we just really simplifying all this stuff down? This has a later implication on when we solve trig functions. When you solve a trig function, the solution to a trig function is an angle measure. So when you're using the identities, you're using the identities to simplify the trig function down in order so that you can solve it. So what you're actually seeing here are like bits and pieces to a bigger piece of the puzzle. All right, any questions about 11? All right, now I'm going to introduce the next section, and it's the sum and difference identities. All right, so I'm going to go back to the lecture notes section for just a second. And in chapter 9, there's something that says sum and difference. Now, I do have a video that deals with the sum and difference. This was like 10 years ago. All right, but there is a question. I mean, there is a video about sum and difference. It's about 17 minutes long. However, I'm going to pull up this 9.2 set of notes. Now, this is not really a proof course, but this is where the formulas come from. And this is called a sum and difference identities. And I'm just going to skip to the formulas. All right, well, here's one formula. right, the cosine of A minus B, this is actually read as a difference of cosine. And the difference of cosine is equal to cosine A cosine B plus sine A sine B. We have also a sum of cosine. The sum of cosine form is cosine A cosine B minus sine A sine B. We also have a sum and difference of sine. So now on the slides, it just kind of shows how all of these formulas are derived. We're just simply going to use the formulas as facts. So if I pull up the all exam formula sheet, on the left-hand side, we have the sum and difference of cosine. The right-hand side, we have the sum and difference of sine. So how and why do you even use these formulas? Well, we use these formulas to find the exact value of an angle that is not in the unit circle. So if you look at this problem, now this should be similar to your problem number one. It says find exact values for the following without using a calculator. The sine of 75. So if I look at my unit circle, I'm not going to find a 75-degree angle, right? I see a 60 and a 90, but no 75. This is where the sum and difference formulas come in. In order to find, let's say, the sine of 75 degrees, I can take any numbers in the unit circle any two numbers I can add to get 75 degrees, or numbers that I can subtract to get 75. So here's what I'm saying by that. I can rewrite the sine of 75 degrees. I can write it as a sine of 30 plus 45, right? 45 plus 30 is 75, right? I could also find 75 if I were to subtract. I believe the 225 minus 75, I think that'll give me like 150. Any numbers I can subtract and any numbers I can add are fair game. So whatever formula you use based upon the number. Right? So here's how I'm going to answer this problem. I want to rewrite the sine of 75 degrees as the sine of 45 degrees plus 30 degrees. Now here again, your classmate may write 30 degrees plus 45 degrees. Your classmate might subtract 2. What matters is as long as he give you 75 and you use the right formula. So this is the first thing. I wrote 75 is 45 plus 30. If I look at my formulas, this is actually move this up a little bit. This would be a sum of sine formula. So if I look at my formulas, this is the sum of sine formula. So this is what it says. I'm going to write it above the problem. It says that put it closer so I can see. The sine of alpha plus beta. Now, one thing, they're using alpha and beta on XYZ homework, but on the formula sheet, I believe this formula sheet is like 8. Yeah, this just has A and B, all right? But on homework, it has alpha and beta. So in this formula, wherever I see an alpha, I'm going to substitute that alpha for 45 degrees. And wherever I see beta, I'm going to substitute beta for 30 degrees. So I'm going to finish writing out the formula. So it says the sine of alpha plus beta, that's equal to the sine of alpha plus the cosine of beta plus cosine alpha. Everybody see what I did? I rewrote 75 as 45 plus 30. And this alludes to a sum of sine formula. So then right above the problem, I just wrote the sum of sine formula. So now the only thing I'm going to do is in this formula, I'm going to replace alpha with 45 degrees and beta with 30 degrees and simplify. So this becomes the sine of 45 degrees times the cosine of 30 degrees plus the cosine of, I'll just do away with these parentheses. Cosine of 45 degrees times the sine of 30. So I found the appropriate formula. I just substituted alpha for 45 and B for 30 degrees. So now I'm going to either use the unit circle or that unit circle function value chart to find these trig functions. So the sine of 45 degrees, if I were to look at the unit circle, I believe it should be square root of 2 over 2. Where is it? It's at the bottom. Okay, it's here. So I'll find 45 degrees. Sine represents the y coordinate. So the sine of 45 degrees is square root of 2 over 2 times the cosine of 30 degrees. So if I look in the unit circle, I'm going to find 30 degrees. The cosine represents the x coordinate. So the cosine of 30 degrees is square root of 3 over 2 plus the cosine of 45 degrees. So I'll find 45 degrees. Cosine is the x coordinate, so that's square root of 2 over 2 times the sine of 30 degrees. So if I find 30 degrees in a unit circle, the sine is the y coordinate. So that should be 1/2. Okay. And now I'm just going to simplify. All right, so we have two terms. For the first term, it's a fraction. So to multiply fractions, I'll multiply my numerators, multiply my denominators. The square root of 2 times the square root of 3 is the square root of 6 over 2 times 2, which is 4, plus I'm going to multiply my numerators and denominators. Square root of 2 times 1 is square root of 2. 2 times 2 is 4. And then lastly, when I add fractions, I keep my common denominator and I combine my numerators. So now just to check this out, right? If I'm going to put my calculator in degree mode, I'm going to put it in degree mode. I can evaluate the sine of 75 degrees. And this is the reason why they want the exact answer, is because it has square roots in it. But if I were to evaluate this, right, the square root of 6 plus the square root of 2. So I'm actually like putting a set of parentheses around that in the calculator. And if I divide that by 4, you get that same exact value. Right, so you use the sum and difference identities to find the exact values of angles that are not in the unit circle.